Hi folks, and welcome back to Physics with Captain Rod. I'm making this video here just to provide some examples of how to apply the right-hand rule as it pertains to finding the magnetic force direction on charged particles moving through magnetic fields. So I'm going to use a standard coordinate system for this, or at least what I call a standard coordinate system for this discussion, with the positive x-axis pointing this way, the positive y-axis pointing this way, and the positive z-axis coming at you. And a little reminder here about the unit vectors that go with those. So in this discussion, plus I will point this way, minus I points this way, plus j, minus j, plus k, minus k. So we're going to go through these examples one at a time. So my first example on the left, we have a magnetic field. I put B sub O minus K direction. What I mean by that is the magnetic field, this should have a vector symbol on it, is equal to some number, that's what the B sub O is, and it's into the board. That's what I mean by minus K direction. Actual values are not important for the discussion. If we have a charged particle, positively charged, with a velocity vector pointing up, meaning this particle is moving through the field this way, to get the force direction, we apply the right-hand rule. And remember, the force direction is Q V cross B. So the force direction is coming from the cross product of the velocity vector crossed with the magnetic field. So you take your hand and your fingers go parallel to the velocity, as straight as you can get it. You rotate until you can sweep towards the magnetic field vector. Now in this problem, the magnetic field vector is into the board, or minus K direction. Right? So now I'm kind of sweeping. Thumb gives you the direction of the cross product. So the magnetic force on this particle is to the left. Put F sub B here. Basically minus I direction. Right. Example 2. We have this positively charged particle with a velocity vector this way, moving through this magnetic field with the vectors I have shown. So the magnetic field in general is some number plus I direction in this example. Actual number not important for now. Okay, so how do we do this one when the angle's not 90? Directionally, you do it exactly the same way. The direction's coming from the cross product. Fingers go parallel to the velocity vector. In this case, that's down at kind of an angle. Now the magnetic field vector is plus I direction. That's this way. So you rotate your hand till you can sweep towards the magnetic field vector. The thumb tells you the magnetic force direction. So in this example, the force is right out of the board, or in other words, plus K direction. There's different ways to draw that. I'm going to go ahead and draw it like this, I guess. And just put all that's plus K direction. What I mean by this is out at you. Boy, I don't know if that quite looks right. Three-dimensional pictures are tough to represent well on a two-dimensional screen. Let's do this. I'm going to draw the force vector as a circle dot. That's a generic way of saying at you when it comes to vectors. So again, there's our magnetic force, and it's in the plus K direction, meaning this way. I'm just going to double check that. Yep. Third example. So here we have another charged particle moving with a velocity through a magnetic field. So again, the velocity vector is describing how fast this particle moves through the magnetic field and in what direction. I think I'll change slides here for this one. Okay, so this magnetic field, I didn't write it out like I did the other two, but it's equal to some number in the plus K direction. So these field vectors, these circle dots, are representing magnetic fields that point this way. So to do the cross product, fingers go parallel to the velocity. We rotate until we can sweep towards the magnetic field vector. The magnetic force on this particle will be this way. Now that's not in the IJK direction, and that's perfectly fine. Right? The magnetic forces do not have to line up with one of our unit vectors. Just a little review. Hopefully you've seen my introduction to magnetic fields, and one of the important points was the magnetic force is always perpendicular to the velocity and the magnetic field vectors. So if you look at this example, the velocity is this way. Right? See, perpendicular, right angle. The magnetic field is this way. There's your right angle. If we look at this example, let me switch sides here. The velocity is this way, the force is this way, there's your right angle. The magnetic field vector is this way, and the force is this way, and there's your right angle. So again, always perpendicular. Over here, one more example. Clearly, hopefully you can see right angle between the velocity and the magnetic force. Also look at the magnetic field is in the board, minus k direction. And it's hard for me to draw, but that's going to give us a 90-degree angle to the magnetic force. So I hope that this video helps at least get you started on how to apply the right-hand rule for deciding on magnetic force directions. Have a great day.